I'll probably take like half of it.
Okay, hi students. So just a reminder again to keep using Lecture Helper. If you feel like your questions aren't getting answered, we're still trying to figure out like the best way to use it effectively. So, just keep asking questions. And if you have any like issues, like any bugs or anything, like just reach out to me personally. And again, the info for logging in is on Piazza. So if you just search Piazza, search Lecture Helper, one word, then you should be able to find it. Yeah. Thanks.
Okay, let's work. Raise your hand if all that stands between you and Friday night is this class. I'm feeling it today. All right. For me, not for you. No complaints. All right. So MP3 is out there. The extra credit deadline is tonight. If you haven't started yet, I strongly encourage you to do so because I really do think MP3 takes longer than any of the other MPs. The debugging cycle is least predictable. Okay, and as Shamila suggested, Lecture Helper is available. I'm going to be able to see your questions here, and I already have a question that if whoever wrote this hadn't reminded me right now, I would have forgotten to address it, even though it's come up several times via email and Piazza. So it's something that I've intended to address, and I just really haven't. The question is about partial credit on exams, okay? So it's an administrative kind of question. So here's the thing. When I talk about exams, first of all, I mean the assessments where you go to the CBTF and you write some code for us. Okay, so when I say exams, that's what I mean. The things that you do in the labs, those are quizzes, okay? Now, for now, the exams are auto-graded, which means that we're not going to see how lovely your code is. The only way for you to show us that your code is lovely is to turn in something that works. Now, we are going to have a set of test cases, and you will get points based on which test cases you pass. And there will be a little bit of credit every single time for turning in compiling code. So what this suggests is that it's a really good practice to do incremental development. That is, first, get the code compiling. Second, work on the first problem. Add features as you go. But make sure after every major change in your code that it doesn't regress, that it doesn't get worse. Now, I know how this feels. It's like, oh no, a little tiny mistake and I get that many points, right? So if this doesn't work out in the end, if the averages are not what we like, we will adjust, okay? So none of this is like doomsday for the class. We'll be kind of calibrating it as we go, and we're not going to give a bunch of Fs here. We never do. So it shouldn't be something that you worry about. I know that's easy for me to say. I know it is, I know. But just keep learning. You're doing the right thing. You came to class on a Friday afternoon. You go. Okay. Boy, I know that's a weak answer. Let's keep trying. Okay, so let's work for just a minute. We were talking about this. And I want you to remind me what it stands for. A, D, T. I'll tell you that the A stands for abstract. What does the D stand for? Do you remember? Data, that's right. Abstract data type. Abstract data type. Okay, so an abstract data type is just a description of the functionality of some model of computation. I usually refer to it as a data structure. So this is an abstract data type, and it is a description of the functionality of a data structure. And lucky for us, in C++, for a given abstract data type, say list, that description of the functionality is included in the public member functions of the class that corresponds to the name of the abstract data type. So all these things kind of go together. Now, what is not included in that description is how they are implemented. That's a totally separate issue. So as we saw last time, I could hide the private section. I can't reach. Normally I would hide it, but I can't reach now. I can hide the private section, and you could still use the class, okay? That's what the abstract data type gives you. It gives you sort of the functionality as a library of the class. All right, today we're going to spend a fair amount of time talking specifically about implementing insert in the context of our new memory model. Now, to describe the new memory model, you might want to take a look here. What's going on there? How would you describe the private members here? If you had to describe it in English very efficiently, how would you describe the way we're storing our data here? What does it look like? What does it mean? What picture would you draw to go along with that? Anybody want to volunteer an answer? How about I'll draw the picture, and then you can be sure that what you're going to suggest is correct. Okay, so what is that? Yeah?
A linked list.
Yeah, that is a linked list. That's right. So we're going to implement our memory behind this abstract data type list here. Our implementation of it is going to be based on linking memory together like this. Okay? Now, you can't see that explicitly here, but there are huge hints that that's what we're doing. Number one, we're keeping a handle on the start of this thing using a list node pointer. Number two, we've got a description of these boxes included in the private section. So while we don't see an explicit drawing of this thing, more like we see an array. When we see an array, there are square brackets, and we kind of understand what's going on. In this context, we see the way we're representing that thing. That is, we can get to all our data if we only have a place to start. Okay? This practice of taking the private section and kind of speculating on what's going on is a really good thing to do, because it gets you thinking about, it gets you in the place of the code from the start. Okay, so given that last week we talked about linked memory, and given that this looks sort of like the structures used in the linked memory, we can look at that and go, oh, look, this list is implemented as a singly linked list. Okay, or chained memory would be another way of saying it. All right, so let's see, a couple other little statements. One thing I want to point out is that this function find, as it was last time, exists for us to use and its role is to simply return a pointer to the node, starting from here and walking that many steps forward. I think for the purposes of everything we use find for, we always start from the head. So find always starts at the head and moves forward, but that's kind of incidental. We can tell it where to start and move that many steps forward. Okay, enough talking. I want to implement insert. Memory looks like this. I want to implement insert. Let's do that. Okay, so how does insert work? Remember that now we're talking about linked memory or a linked list as data associated with an object. So what's going to happen is we're going to declare ourselves, in this case, a list of integers, and I'm going to call it L because I'm creative like that. And with that list, we can do L dot insert, inert, into position K. Oh, I don't know. I think I'll do an insert into position 3. What integer would you like? Alec, tell me an integer. 5. Okay. Like this. And I'm going to say insert a bunch of stuff so that memory looks like this. And then we're going to call L.insert into position 3, value 5. Okay? Now, this box here is the head, and this is the state of memory when we do this command. Now, somebody volunteer to tell me, in that data, where does 5 go for this insert? Where does 5 go? Insert into position 3, value 5. Yeah? Yeah, I think so too, between 6 and 4. So we want, in the end, here I'll do it in a strange color. In the end, we want to write code that would make a box, this is funny, value 5, and it would look like this. And I'm making it look funny like that because we haven't done the work yet. That's just our imagination, right? We're going to make it look like that eventually. Okay, and I agree that that's where we would want it. Now, how did I know to put it there instead of after the 4? This harkens back to the experience we had last time where we reminded each other, I think, that we're writing code for the client. That is, when you say the third position in a list, the first position is the first position. There's no such thing as a 0th position. That's anxiety that we should just get rid of. Okay, so when we talk about the third position, we mean the first, second, third. Okay? All right. So let's write code to make this happen. Now, this strategy for inserting is pretty common. We're going to follow the following paradigm. We're going to create a new node, because we're inserting, so we know we're going to need one. We're going to create a new node and then fix up the pointers. Okay? Create a new node and fix up the pointers. So here is the code to create a new node. Here's the code to create a new node. So what does this do? It takes declares a pointer whose name is T and uses it as the handle on a new list node whose value becomes 5 and whose next field is null. So after that line, we've got part of what we're going for, right? All right, now let's follow the code. if k is equal to 1, we're going to do something a little bit different, and I'm going to ask you why in a little bit. So I want to handle this case first, the general case first, and then I'll come back and I'll ask you why that special case exists. So let's trace this code. We are going to position a new pointer whose name is P somewhere. Where would it be very handy to have a pointer? Where do you wish you had a pointer? I wish we had a pointer pointing to which box? The box containing what data? 6. Yeah. Yeah, right. Okay. So I wish, so I should put this in yellow because we don't have it yet. I wish we had a pointer to the box containing 6. That would make me really happy too. I'm going to use find to get there. I'm going to use find to get there. How many steps forward do I walk relative to k? Relative to the input parameter, how many steps forward should I walk? Yeah? You want to say k minus 1. Raise your hand if you really want to say k minus 1. You want to say k minus 1. Okay, this is going to be humbling. I hope you're ready for this. Anybody want to suggest it? Oh, what the? Really? Yeah, look. Even in our example, k is equal to 3, right? We said put it in the third spot. We want the pointer to the spot before, and find walks forward a certain number of steps. Find is going to start at head and walk forward how many? 1, right? 3 minus 2 is 1 step. Now, what's going on here? It's sort of an indexing trick because any pointer that you have pointing there means walk forward 0 steps, right? So it's walk forward 0 steps to get to the first thing. So that's where that kind of off by 1 error exists, okay? I don't want to spend a whole lot of time on it. You'll see why in a second. All right, so now we have this pointer to the place that we like. Yeah? Uh-huh. So I think that there are scenarios where we would have a different implementation of find, but our implementation of find is clear. It's wherever we start, walk forward, k steps. Okay? You are right that if we indexed our whole thing differently, if we said point to the kth thing, that would be different. That would be a different find. Does that make sense? Okay. All right, so for now, we have k minus 2 here. But the good news is that gets us ready to do all our pointer fixing. So the first pointer that I'm going to change is t next. And what I want it to do is go from what it was before and become that. What value gives me that? What assignment gives me the right thing for t next? P next. Yeah? And to judge that, I look around this box. I go, okay, here's the box. What else is pointing there? Well, this pointer is pointing there. What's the name of that pointer? The name of that pointer is P next. Okay? And now, our last one that we need to fix up is this one. P next should get the value of t. Very good. Okay, any question about that piece of it? Okay, seems okay. All right, so now let's talk about this special case for a second. Why do we need that special case? Why do we need, yeah? Because head is not a list node itself, that's true, but it points to right, very good. In fact, what's P if we use this code? What's P? What's list node pointer P equals find of head of -1? Ew. We don't know how to go backwards. Our find doesn't work that way. I don't know what -1 means in that context. So find of -1, meaningless. We have to have a different way of handling the case where k equals 1. Now, furthermore, notice, as he said, what we depended on in this scenario is the ability to set up a pointer pointing to the node before, right? We needed a pointer pointing to the node before. What's the node before the first thing? There isn't one, right? There is no node before, as he said. So we have to do it differently. Insert at front is, we wrote it last time. We wrote it last time. And it involves just resetting head. Okay, it's still this to fix up pointers process. Yeah, there may be a little bit of a bug there. We insert at front. Insert at front should be written in such a way that it doesn't redeclare T, okay? Well, we can fix this up, but we're not going to, okay? That's slightly broken as it is right now. It would declare 2 new list node pointers because insert at front makes its own. So after all these years, I have never noticed this bug before. So thank you to whoever asked. Does this have a memory leak at k equals 1? Well, yeah, it does because of this reason, because we're actually making 2 new nodes, okay? We don't need to. But all of this is a mess. Anyway, we shouldn't do this. Look at that code. There's this conditional there. There's an if statement that makes a special case out of inserting at the front. And I don't know about you, but every time I see an if statement, I go, uh-oh, that's got to be a problem because I have to make a new test case for every branch of my conditional. Now, I don't know how you feel about making test cases, but I hate it. I hate having to go, okay, well, in order to test all this code, I need to make a test case for true and for false in my conditional. And test cases are not, I mean, I probably shouldn't say it, right? I shouldn't be allowed to say it. But here's the thing. What we're going to do is rethink the problem in such a way to eliminate the special case, if we can do so. All right? So we want to rethink the problem in such a way to eliminate the special case. All right. Before we go there, though, I want to analyze the running time of this thing. It's going to be this is an aside. So for the running time, how long does it take to position that pointer before the one you want to insert? How long does it take in the worst case? Big O of n. Right. The way you evaluate that is to pretend like your worst enemy is giving you k. Your worst enemy, that is the person who wants this function to take as long as possible, is going to give you the value of k. And they're going to give you n. Put it in the last spot, right? Okay. So that is linear time. And the way I'm going to describe the reason that it's linear time is to say to find. Okay, because we have to find first. Okay, how about in an array? Let's suppose we have an array that looks like this. And we want to insert something right there, say. What's our scheme for doing so? Our scheme for doing so, do you remember? How do we do it? Yeah? Yeah, you have to make space for it. Oh, how do you do that? You have to move stuff down, that's right. And moreover, what does that look like? It means get that one out of the way, which means get that one out of the way, and get that one out of the way, and get that one out of the way, and then you can enter the value you want. Okay? So this one is also big O of n, but this time we describe it as big O of n to shift the data. Any question about that? So both of them are big O of n, but they're for big O of n for different reasons. Any question? Is that okay? All right, so let's go back and revisit the elegance issue. That is the goal of eliminating that special case out of the if statement. And this is why I'm not too embarrassed about messing up the insert at front thing. Well, this is interesting. Here's what the picture means. The picture means that we are going to, at the front of every single list, we are going to put a single buffer node called a sentinel node. Its purpose is basically just to be in front of the list. It's a marker that says, hey, I'm in front of the list. That's all. Okay? That means that an empty list is no longer a null pointer. An empty list is this sentinel node, and that's it. Okay? Now let's look at what it's like to insert into this list. And we'll do the same thing. What was it? Insert into L.insert into position 3, value 5. Okay? We still want to do the same thing where we create a new node and put in the value 5. And looks like we called it T. Okay, so we do the same thing here. And we are still interested in setting up a pointer to the node before. This time we called it cur instead of P. I don't know why. And the question is, how far do we have to walk this time? K minus 1. This time, K minus 1 works. Because every time we call find, now, we're walking one step farther. So instead of minus 2, it's minus 1, right? Because every time we start at the head, we're going to have to step over that sentinel node. So this time, find goes K minus 1 steps. Okay? And now we just have to fix up pointers. We've got names for everything we want. We just need to fix up the pointers. T next equals, T next gets the value of, I want it to look like this. How do I do that? Cur next, good. Okay, and then cur next gets T, just like we saw before. Good. Any question about that? Any question about it? Yeah? How do you? The question is, does the sentinel node ever have a value? Garbage. Okay, the sentinel node is the garbage value of whatever the list item type is, whatever the templatized type is, or the default value. And you construct that in the constructor of the list node. Okay? All right, fine. Let's see. Any other questions about this? Where'd the if statement go? That insert at front now is not a special case, because what's true no matter where you want to do an insert is there's always a node before. There will always be a place to set up that pointer cur that we have here, because that sentinel node plays that role. Okay? Did you have a question? No? It's okay? All right. So how do we make this happen? Well, what's the answer? How do we make this happen? What do we deploy to make this happen? What is this? It's the list constructor. So that when we say list, I guess in this case it's int L, we want to set it up so that memory looks like this. So this thing is called head, and it has a node whose value we don't care about. There's an empty list. Look, there's an empty list. That is the sentinel node. Okay? So let's write that code really quick. It's just head equal new list node. And that's it. That's all we have to do. I guess we should still set the size equal to 0, because we still want size to denote the amount of data in the list, not the number of nodes, the amount of data in the list. Okay, any questions about it? What's the running time of insert? It's still big O of n. Okay, we didn't really fix that. We just made our code less complex. This idea of thinking about how you can use memory to make your code less complex is a really good skill to have, because it means that you will write code that's easier to debug and less likely to have bugs to begin with. Write simpler code. Okay, case in point, the previous one actually was buggy. Okay. Any questions about it? You okay? All right, so now I have another little one to show you, another little trick to show you. It's most closely related to the remove function for lists, but it's a little bit different. I'm still going to call it remove current. I'm going to call it remove current. So that's something different than the remove function in the list class. You could use it in the remove function of the list class, but probably you wouldn't need to, because here's what I'm going to do. I'm going to describe this in a way that's sort of strange. This function, remove current, takes a pointer to exactly the node that you want to remove. So let's say, for example, that we want to remove that one. I'm going to tell it to you via the parameter. So that's what the parameter is to remove current. Remove that one right there. Okay? Any question about that? Now that's a little different than the remove that we had in the list class, because that one says remove from a position. Okay, so let's talk about implementation here. Where do you wish you had a pointer? Can we just remove that one? Can we just do this? Can I just say delete cur? Can I do that? I can't, but I gave it to you. I just want to delete it. What happens? Like a broken heart, right? We break our list in two. We've taken a node right out of the middle of the list. So that's not the strategy. Nope, not doing that. Okay, fine. What do we need to do? we need to hook up the pointers around cur, right? We need to effectively do this. So where do we wish we had a pointer? Where do we wish we had a pointer? Where would it be helpful? To the node containing 2. That's right. So I'm going to write it like this. I'm going to write this as wish. Okay, how do we get wish in this scenario? How do we get wish? I give you cur, and I want a pointer to this node. How do I get it? Oh, it's not a doubly linked list. There is no previous. Your only alternative is to go all the way to the start of the list and walk forward until you get there. And you notice that I put some ellipses there, right? We don't know how long this list is. It could have a gazillion nodes, or it could have 4. We don't know. The point being that even though I tell you exactly what node I want to remove, you have to go all the way back to the beginning and iterate down the list so as to get a pointer to that node before. Okay, so let's write that code really quickly. Let's see. So I want list node pointer wish. And I'm going to start it off at the head. And while it's next, wishes next is not equal to what? Cur, very good. I'm going to walk it forward. Wish gets wish next. How do I know wish is not equal to null? How do I know that wish is not equal to null? I just dereferenced wish in that while statement. Did I just dereference null? Could I have? I can't. Why? Because there's a sentinel, right? Head will never be null. I never need to worry about it. That's kind of cool. Didn't have to think about null there. Yay. All right. So walking forward, perfectly fine. Wish next could be null, but I never, if cur is not equal to null, then wish next won't be null. Okay? All right. So I've walked forward wish until it's the one before cur, and now I've got everything I need to fix up the pointers. So I can say, wish next equal her next, yeah? Her next. And that does this. And then, what letter am I going to write next? D, good. Delete cur. Okay, any question about it? When I say any question, now's a really good time to type your question. If you feel like you have a question, but you don't want to ask it, I really am seeing them, and I'm trying really hard to like incorporate the questions into the flow. Okay, any question about it? Yeah? Really good question. Can we use the find function? The question is, can you use the find function? And the answer to that is, we could if we knew how many steps to walk it forward, but we don't know that in this context. In this context, we happen to only have a pointer to the place, not any notion of where it is location-wise. Okay? All right, any other question? Yeah? Could I put cur in the find function? Oh, no, no, I don't know. Cur or find demands a number of steps, right? But cur is not an integer. Cur is a pointer. Cur is a list node pointer, right? Yeah. Okay, this is a little artificial because usually you're going to know an identity between, how far things are, and it's a little weird. And you wish you had that pointer to begin with. Now, do you like this code? What's the running time of it? Big O of n. So that's bad news, right? Because I told you the pointer that I wanted to, I told you the node that I want to move. And you say, oh, wait, okay, we'll remove it. And you have to do all that work. Okay, fine. So let's try again. I want to remove that node. I think the description is a little easier if I remove. What did I say last time? My example was, yeah, okay, I'll do it the same. I want to remove that node. URR. Okay. What node would be easy to remove? So we've kind of shown how to remove the current node. What node would be easy to remove? Yeah, the next node, right? Okay, the next node would be easy to remove. What value do I want to remove from the list? I want to remove what data? 7. But the next node is really easy to remove. So, anybody have any ideas how I might rectify this confusion or this situation? What? Oh, look. Watch. Watch this. I'm going to grab this one, copy its data, reattach this, which in this case means setting it equal to null, and then delete this guy. Whoa. Kid you not. Let me write the code for that really quickly, and then we'll talk about it for a second. Okay? So the first thing I want to do is be sure to grab the next one. So I'm going to say list node pointer t equal cur next. I'm going to assume cur is not equal to null because it's going to point to something that I want to remove. Okay? And then cur's data should get the value of t's data. I know that you all have problems with this. And cur's next should get the value of t's next. And then I can say delete t. I think there are a couple things to be said here, at least two. How do you feel about this code? How do you feel about this code? Yeah? So all of them will be integers in the list because the list itself is templatized to contain a particular type. We instantiated it as integers. Okay? So it will always be the case that across that assignment, the things are the same, okay? Unless it's an inherited, if you get into trouble, the compiler will help you with templatized types, okay? All right? Yeah? So you are worried about this line right where? Which line of code are you worried about? 2 and 3? You're worried about this being null, t being null. Right? Because then you dereference it and then you're in trouble. So what would be the circumstance if t was equal to null? What would be that circumstance? Yeah? Very keen observation. So the thing you should be worried about is if t is null, which means it's the same thing as cur next equal null, or removing last item of the list. Okay, that's what you should be worried about. I think you have all the tools you need to fix that. How could you fix that problem? How could you fix that problem? Yeah? With an if statement. Do we like if? Right, we can test. We can see if the special case, were true, that we're pointing to the last thing of the list. Do you like that? How do we feel about if statements today? We don't like if statements today. So how might you fix it? Say it louder. We can use a sentinel node. That's right. Very good. So what we can do is put a yellow node right here whose value is essentially garbage, and we can allow that to be, the last node. You know it will always exist because you're never going to try to remove it. It's like a bumper on the ends of your list. You've got one at the start and you've got one at the end, and all your data goes somewhere in between. Okay? So now somebody might ask you to implement the constructor for that, and what you would have to do is figure out how to make head look like this. Now that's garbage. That is garbage, and the last thing is null. You've got what we refer to as the head sentinel and the tail sentinel, and all the data that you ever insert into this thing will go in there. Okay, and that solves both of the problems. Okay, I think there's another problem with this code, though. And I'll give you a hint that it has to do with this line. Yeah? Yeah, look. Right, really good. So we can count on being able to do the assignment there because assignment operators work, right? But it might be very expensive to do so. That data could be a really big thing. It could be a photo album, right? Like, it can be anything in this context. So the data copy could be expensive. Very good. Okay, and the last thing is extremely subtle. Imagine if your closet, if you were so type A that every night when you got home and you took off your shoes, you put them in your shoebox in your closet, in their shoebox in your closet. Okay? So you've got all your shoe boxes in your closet and all your shoes in your shoe boxes. Okay? Now, if I came to you and said, put on your sneakers, we gotta go, you would know exactly where your sneakers were because of the box that you put them in, right? Well, here's what we're doing in this example. We're taking the sneakers we're taking the boots and we're putting them in the sneaker box. That is, we're taking the data out of one place where somebody might depend on it being, and we're putting it into a different box. we're destroying the identity between the node itself and the data that that node contains. Later on, when we talk about iterators, we'll understand what it means for an iterator to be invalidated. That is, the thing that depends on, a thing that depends on the integrity of the box and the identity of the data within it will no longer be relevant. That observation is why we call this a hack, because it destroys that relationship between the shoes and the box that they live in, the data and the box that it lives in. Okay, happy Friday.